Okay, in this section 3.5, we're going to talk about standard minimization problems. And basically, with a standard minimization problem, what we're going to look for is how to solve a problem that we're strictly asked to minimize the objective function and the constraints are of the form greater than or equal to. So this is just the opposite of what we solve using the simplex method. Now, before we get too deep into it, let me just tell you there's two phases to solving problems using the dual method. The first phase is to actually know how to find the dual method from a problem like one of these that's listed here. But the other method, the other phase that we have to talk about is how do we find, once we get the dual method, how do we solve it? So I'm going to do this in two videos. So this video is going to focus on taking some problems and converting them to their dual problem. So let's get started on that. Now, one of the things we're going to have to do to convert to a dual problem is we're going to have to take a matrix and we're going to have to transpose the matrix. You can read the instructions up there, but it's pretty simple. If I want to transpose this matrix, what I'll do is I'll take this first row 1, 3, 15 and then I'll convert it to the first column. And then I'll take the second row, which is 2, 1, 20, and I'll convert it and make it the second column. And then I'll take the third row here, 5, 2, 1, and I'll convert it to the third column. So it's kind of like we're turning the matrix sideways in a sense, but we're just converting the rows to columns. And in a sense, that's converting the columns to rows. One thing that I thought I'd show you just real quick, if you were to take the transpose of the transpose, it would actually take you back to the original matrix. But that's really not that important here, but I just thought it's an interesting fact. Okay, so now what I'd like to do is go to a standard minimization problem and see how this transpose comes into play. So if you will look right here, you'll see that I have a standard minimization problem. I'm minimizing and my constraints, both of these constraints are in the form greater than or equal to. Now, let's focus on the constraints. These are the two constraints. And let's write the objective function, but let's write it from right to left. So here's the first constraint. Here's the second constraint, and then here's the objective function written right to left. Now, focus on these coefficients. The coefficients for the first constraint are 1, 3, and 15. The coefficient for the second constraint is 2, 1, 20. And the coefficients for the objective function are 5, 2, and 1. So we're going to treat C as just 1C. Now what we're going to do is we're going to write this in a matrix. So let's call that matrix A. So put the coefficients of your first constraint in the first row, 1, 3, 15. Second set of coefficients in the second row, 2, 1, 20. And in the bottom row, 5, 2, and 1. Now, I wrote 1C, but your book may not write that. Your book might write 1. Some books might even put 0 there. This is really just a placeholder for when we get the transpose. Notice I listed at the top of each column which variable these coefficients represent. So these represent the coefficients of x1 and these represent the coefficients of x2. Now I'm going to transpose this. So when I transpose this, 1, 3, 15 becomes this column, and then the row 2, 1, 20 becomes this column, and then the row 5, 2, 1 becomes this column. Okay, now the reason I wrote P here is because when we get the dual problem from this transpose, and that's where we're going to get it from, what we have to do is we have to change all of our variables. So notice above this column I wrote y1 and y2 instead of x1 and x2. And so instead of using C for my dual problem, I'll use P. And what I'm going to do now is I'm going to take this transpose, and from this transpose I'm going to actually get the dual problem. So let's take a look down here. Here's the transpose again, is rewritten. Okay, now let's talk about what is a dual problem. By definition, a dual problem is a standard maximization problem. So when I say standard maximization, you know that I mean we're going to maximize a problem with less than constraints. So I'm going to use less than or equal to constraints. So I'm going to take this transpose, and from the bottom row I'm going to get the objective function that I'm going to maximize. And that's going to be P equals 15y1 plus 20y2. So my new objective function becomes P equals 15y1 plus 20y2. And then my two rows above here are going to be my new constraints. But remember, we're using y values. So I'm going to have y1 plus 2y2 is less than or equal to 5, and 3y1 plus y2 is less than or equal to see, is that right? Should that be 1? I copied that wrong here, right? It should be a 2. Okay, it's right over here though. So 3y1 plus y2 would be less than or equal to 2. Okay, so now the other thing you don't want to forget is your variables y1 and y2 also have to be non-negative. So if I were to give you this problem here and ask you just to convert it to its dual, you would go through these steps, but your answer would be this, everything that's in this rectangle here. That would be the dual problem. So again, the original problem was minimization with greater than constraints, and the dual problem must be maximization with less than constraints. And that's how you set up the dual problem from a standard minimization problem. Okay, let's look at setting up the dual one more time. You'll see here I have a minimization problem, and my constraints are greater than or equal to. And so what I'm going to do is I'm going to take the coefficients from the first constraint, 2, 1, 5, and 20, and that's going to be my first row. And then the coefficients from the second constraint, 4, 1, 1, 30, that's going to be my second row here. And then the coefficients of my objective function, 40, 12, and 40, are going to make up my final row, and the 1 just stands for 1C. Now, one thing you don't want to remember is this is not, we're not setting up a tableau. This is just a matrix. So we're not moving these terms across the equal sign here and changing signs. So we just copy these down just as they're written, 40, 12, and 40. Alright, then I want to transpose the matrix so that I can get my dual. So I transpose this, 2, 1, 5, 20 becomes this column, 2, 1, 5, 20. The second row, 4, 1, 1, 30 becomes this column, 4, 1, 1, 30. And the third row becomes the third column, 40, 20, 40, and 1. Now, notice that I have 3 rows above the objective function. Alright, now remember, this is the objective function, and this gets converted to new variables, right? So we convert it to a maximization problem where we have P equals 20y1, not x's, but y1 plus 30y2, and that's your objective function. Now notice here, I actually have 3 constraints here. 1, 2, 3. So this one's going to be 2y1 plus 4y2, and remember we use less than or equal to. So it's 2y1 plus 4y2 is less than or equal to 40. And then this one's going to be y1 plus y2 is less than or equal to 12. And then the final one is 5y1 plus y2 is less than or equal to 40. Again. So now, there's the dual problem. So again, if I had asked you for the dual problem, you would stop after you set up this linear programming model. Now, one thing I do want to caution you of, you can have different number of variables from your original problem to your dual problem. Notice in my original problem, I have 3 decision variables, x1, x2, and x3. But in my dual problem, I only have 2 decision variables, y1 and y2. That's because the number of decision variables that we end up with here are actually related to how many constraints we have in the original problem. Since we had only 2 greater than constraints, then we're only going to get 2 decision variables here, y1 and y2. So that's another example. So that completes the second example of setting up the dual problem. Okay, I'll show you one more. Here we're minimizing and all the constraints are greater than or equal to. So we want to write the coefficient matrix, which is A, and the first constraints are 3, 2, 2, and 16. So that's the coefficients of the first constraint. Coefficients of the second constraint are 4, 3, 1, and 14. So that's going to be our second row. The third row is 5, 3, 1, and 12. And then my bottom row comes from the objective function coefficient, 16, 8, 4, and then 1 for 1c. And then I transpose this, and so by now you know how to transpose it. And when you transpose it, you're going to get this matrix. And then from this matrix, we look at the bottom row to get our objective function. And so our objective function is going to be maximize P equals 16y1 plus 14y2 plus 12y3. So that's over here. And then the other 3 rows represent my constraints. Now remember, I'm converting to a standard maximization problem, so these constraints must be written in less than or equal to form. So 3y1 plus 4y2 plus 5y3 is less than or equal to 16. 2y1 plus 3y2 plus 3y3 is less than or equal to 8. And then 2y1 plus y2 plus y3 is less than or equal to 4. And again, there's the dual problem. Now, in the next video, in this video, again, I'm just showing you how to set up the dual. In the next video, I'm going to show you how to solve the dual to determine the solution to the original problem. And here's what's really good about this dual. The dual is always a standard maximization problem. And remember, we learned that you can use the simplex method to solve a standard maximization problem. So I'll explain to you how this fits together in the next video when I show you how to solve these dual problems for the solutions to the original problem.